organic reactions. Now, organic reactions are, now that you understand intermolecular forces and you understand how to name compounds, you understand the different functional groups, homologous series, these molecules are not in isolation. They take place in their own kind of reaction. So just like how we have normal chemical reactions, we have organic reactions. Now you've got 5 types of reactions in total. You've got combustion reactions, addition reactions, elimination reactions, and condensation reactions. Now, of this list, it helps if you go to the note pack that I asked you guys to collect. The note pack goes, I think what we want to look at is page 60.65. Now again, you want to use this video to create memory, muscle memory. You want to use it to practice structural formula, semi-structural formula as I go through it. But also you want to engage with it. It's not just theory that you can just memorize. It's also a little bit of practice. So as I'm going through this section, take down the notes, have a look at the examples that I'm doing, pause the video, try and make decisions about what products are going to be formed if you're looking at base formula. So what you need to understand is the base formula. You need to understand where does it fall under. So combustion reactions and condensation reactions, there's just one reaction. But addition, elimination, and substitution have up to 3 or 4 different types of reactions within that. Now, when you're given this section, it is not in isolation. Again, every single reaction in this list is related to each other in some way. So it can form a flow chart, which I'm going to show you how we draw up the flow chart, and that is how it's asked in a test or an exam. So take the effort to make sure that you've got everything that you need and that you're practicing and that you're not just listening. You're actually writing things down so that it becomes part of your own version of information. Right, the first type of reaction we have is a combustion reaction, in other words, an oxidation reaction. This reaction you've come across quite often, and you have been exposed to certain types of alkanes in these types of reactions in grade 10 and 11. Now we're going to actually have a look at how we draw these out or what structural formulas look like. So they can ask you to draw structural formula, molecular formula, whatever the case is. So a reaction that is a combustion or oxidation reaction is the reaction of oxygen with alkanes, alkenes, or alkynes. For example, here I've got ethane plus oxygen gives me carbon dioxide and water. So it's always, you're always going to have a fuel. So you're going to have some sort of fuel plus your oxygen, and your products must be carbon dioxide and water. So if they had to ask you to draw a structural formula, for example, I can do methane plus oxygen gives me carbon dioxide and water. And they can ask you to draw the structural formula of that. Methane, single carbon, 4 hydrogens. Remember, when you're drawing structural formula, everything must be in a structural formula. Oxygen will have a double bond. Carbon dioxide is, and you make sure you draw these notations correctly, and you draw the shapes. Oops. Correctly as well. So that is the word equation. And over here we have the it's an unbalanced structural formula. You will then need to balance this equation and make sure that you indicate how many of each of these molecules you have. So that is what combustion reactions about. Not something unfamiliar, something that you have done before, and an example of how you write out structural formula for combustion reaction. Right, the next type of reaction you have is addition reactions. Now, addition reactions, they take place in unsaturated compounds like alkenes and alkynes. So what we want to do is we want to break the double and triple bonds between the carbons, and then we want to produce a saturated molecule like an alkane. Now these types of reactions, addition reactions, they take place at a higher rate of reaction than substitution reactions. In other words, they are faster than a substitution reaction. So we've got a list here of different types of addition reactions. There's a base formula, and I'll show you an example of each one, structural formula or semi-structural formula, so that you can start getting a little bit of practice of how this needs to be done for tests or exams. Alright, so the first reaction we have is hydration. Hydration is an alkene plus water gives me alcohol. So for example, if I had ethene plus H2O, I should get ethanol. So if I had to draw ethene, I need a double bond between the carbons. So this is the structural formula plus water. Please make sure you get these shapes right. Is going to give me ethanol, so 2 carbons. And you've got an OH. So what you want to make sure that you have is you want to make sure that your product has an OH. So all that's happening here is that the bond over here between the 2 carbons, that bond breaks, right, leaving us with each carbon having an extra hydrogen or an additional functional group. So if I look here, this hydrogen over here comes from there, and this OH over here comes from this OH here. And that is how I get an alkene and water to turn into an alcohol. Now, what you want to make sure you do is the reaction conditions must be also mentioned in your equation. So how we do that, because it's a catalyst and there's excess water, so we must mention the catalyst. So all we do when we mention the catalyst is we indicate above this arrow, the acid here is H3PO4. You indicate that acid. So this is showing me the catalyst. It goes above the arrow. So you'd put it there, or you can put it there. But the catalyst must be present. The second reaction we then have is halogenation. Okay. Now halogenation is if we start off with an alkene and we add to that alkene some sort of diatomic halogen. So what you're looking at here is a diatomic halogen, and all your halogens are diatomic. So F2, Cl2, Br2, and I2. The X here refers to a halogen, which can be F, Cl, Br, or I. Okay, but it's always in its diatomic form. And what you want to form at the end is a haloalkane. So for example, if I started off with an alkene, so I'll start off with the most basic alkene. And remember, I'm drawing it in different ways to show you that there's different ways of drawing alkene. So I've got my double bond between carbons plus a halogen. So if I pick, for example, bromine, so it's Br to a Br. I'm doing structural formula. And I get a haloalkane, which is going to look like this. And I've got hydrogen, hydrogen, a Br would be here, another hydrogen, a hydrogen, and a Br here. So what happens is that this bond here needs to break. So that's what we want to see here. The bond breaks, which gives us then the single bond in the haloalkane. And then each Br, where that bond broke, each Br takes that position. So you add an alkene to a diatomic halogen and you'll end up with a haloalkane. And for this reaction, you need an unreactive solvent, which means that no water is present if you have halogenation. Okay. Another thing that's a side note to all of this is we can say, so something that's important to remember, if you have rapid decolorization of bromine water, by an alkene at room temperature, that will be a test to distinguish between alkanes and alkenes. And in that note pack that I gave you guys, you will find it after these types of reactions. You'll see all the tests. So this is what we call a test for unsaturation. So that's just a little bit of a side note. Okay, so that is halogenation. All right, then we've got hydrohalogenation. Hydrohalogenation is if I start with an alkene and added to that alkene, I've got a halogen salt, a halide salt, and what I can get from there is a haloalkane. So once again, like I said, this X here represents a halogen. So if I had to start with an alkene, I could start with something like propene. So if I drew propene out, so I've got your propene plus, let's say, hydrogen bromide. What that turns into is a haloalkane. So again, the double bond here, the double bond over here must break. And once that bond breaks, you end up with a compound that looks like this. Which is your haloalkane. And we need to name this haloalkane. So the bromine's on the second carbon, so we're going to go 2 bromo propane. So that's how you name that situation. Okay. All right, and the reaction conditions for this is that there must be no water again, and an unreactive solvent. Then the fourth one you have is hydrogenation. And in hydrogenation, you start off again with an alkene. You add a hydrogen molecule to it. So just remember that this is a diatomic. Always the diatomic stay diatomic, and you're going to get an alkane out of it. So again, I can start off here with ethene plus hydrogen, and that's going to give me an alkane, because that double bond is going to break from ethene, and I'm going to end up with ethane. Now, the reaction conditions for hydrogenation is that there must be a surface catalyst. So like I said before, what you want to do is above your arrow, you must put in whatever surface catalyst you use. Platinum, palladium, or you can even put nickel, whatever the reaction, whatever catalyst this reaction requires. It's called a surface catalyst. So you put the reaction onto a surface, and the surface actually, and we did catalyst last year, it actually holds on to the molecules a bit better. It keeps them in the correct orientation so that the reaction can happen in a better way. The other reaction condition that must be met is that it must take place in a hydrogen-based atmosphere for this reaction to take place. And the next type of reaction that we have is elimination reactions. So what we call an elimination reaction is that it must take place between alkanes and haloalkanes. So what the major thing is that you're going to take a larger molecule and break it into smaller molecules. So 2 atoms are removed from a saturated compound to form an unsaturated organic compound with a double bond. So in the previous one with addition, we went from having double bonds to single bonds. Here we have single bonds, and we want to take those single bonds and make them into double bonds. Okay, so the first reaction that we have for elimination reactions is a dehydrohalogenation of a haloalkane. So dehydro means that you must have a situation where something is being removed. So the product here that is formed is when a hydrogen atom is removed from a carbon atom that has the least number of hydrogen atoms attached to it. So I'm going to show you an example of that. Okay, so if I had a haloalkane, I could have CH3CH2Br, and that is bromo ethane, and that would give me an alkene. So it would give me CH2 double bond CH2 plus NABR. Now you're wondering now, where am I getting that NABR from? Okay, so if I look at my reaction conditions, it says here that you must have a concentrated or strong base, and ethanol must dissolve the haloalkane and heat it under reflux. Okay, so when I have that, so I'm going to end up with ethene plus sodium bromide. Now I need to indicate where I'm getting this NABR from. Okay, sodium bromide. So what we do is, over the arrow, like I said before, we need to put in I'm getting NABR. So the base that I'm using is NaOH. Okay. And they're saying that you must have ethanol. So I will write here ethanol. Is ethanol. Okay. Another way that this can be done is I can say CH3CH2Br plus NaOH, arrow ethanol gives me CH2 double bond CH2 plus NaBr. So that's fine too. The other thing that needs to be mentioned above your arrow is it must take place with heat. So you can write the equation either way. You just need to remember that above your arrow, whatever is missing needs to be mentioned. Now it says here that it's being heated under something we call reflux. So what does reflux mean? Reflux means, so reflux is a technique used to apply heat energy to a chemical reaction mixture over an extended period of time. So that is what it means for reflux. And in these types of reactions, again, I've got all my conditions. I must just remember as well that no water must be present in a dehydrohalogenation reaction. Okay, the next type of reaction that we have, remember you can always pause, take the notes, work with it, get that muscle memory in. So this is a different type of structure that I've used. So if they ask for structural formula and you write a molecular formula, it will be marked as incorrect. What we have here is a condensed structural formula, semi-structural formula. If they ask for semi-structural formula, you have to write semi-structural formula. You have to understand each type of way of how to write these formulas out. If they ask for structural and you do semi-structural, it will all be marked as incorrect because you are not reading the question. All right, the next type of elimination reaction is a dehydration reaction. So with dehydration reactions, you're going to have the elimination of water from an alcohol, creating a product with a double bond and water. So you start off with an alcohol, you end up with an alkene and water. And remember, the product that is formed when a hydrogen atom is removed from a carbon atom that has the least number of hydrogen atoms attached to it. So let's have a look at an example for dehydration. Okay, so if I have a look, I can draw propanol. And I have, for example, so if I put all of this in, I'm just going to show you how this all works out. So I start off with propanol, and then my propanol becomes propene, and that gets 3 hydrogens. This gets 1 hydrogen. And this gets 2 hydrogens. Okay. So I started off with propanol. And I ended up with propene. Plus, if you look at the blue, I ended up with, oops, H2O. So for a dehydration reaction, you start off with an alcohol, and here you can see here which part of the alcohol is going to be eliminated from the alcohol. You end up with propene, so there's your double bond that was created, and the atoms that were eliminated from the propanol, from the alcohol, becomes your water molecule. Now, for a dehydration reaction, your reaction conditions is that a dehydrating agent needs to act as a catalyst, which is H2SO4, and you've got to heat the alcohol with the concentrated catalyst. So what we want to do is, above our arrow, we want to put in H2SO4, and we want to also put in that this reaction needs to be heated. So make sure that you indicate your catalysts and your reaction conditions above your arrows. Make sure it's done. Otherwise, you don't get the marks for those types of questions. And then the last thing we're looking at is cracking of alkanes. So number 3, what we do here is we break up a large saturated hydrocarbon. Saturated hydrocarbon, remember, are alkanes, into smaller, more useful molecules. So the products are always an alkene or an alkane. There's 2 types. So you start off with an alkane, and then you can get a short alkane and an alkene. So you must get smaller molecules out of it. It's not always just an alkene. It varies depending on what alkane they've given you. Now there are, for the reaction conditions for this one, there are 2 different types of cracking that takes place. Please remember to pause the video, take down your notes. Don't just watch it, like I said, don't just watch it like you're being mindless. These are the types of things that you're going to be asked in test week, and you're going to need to make sure you understand every kind of reaction and how it works. So get that muscle memory in and make these notes your own. There's really no point in watching it if you're not actually engaging with the video and the information. So there's 2 types of cracking. The first type is catalytic cracking. That takes place at a low temperature and a low pressure with a catalyst. The 2 catalysts you can use is silica or alumina. And then there's thermal cracking. That takes place at a high temperature and pressure, but there's no catalyst involved in this situation. Remember, high temperatures, if I have high temperatures, that increases the rate of the reaction. If I have low temperature and pressure, I need a catalyst to make that reaction happen faster. So if I have something at a high temperature and pressure, there is no need for a catalyst, because if I have a high temperature, my reaction is going to go faster, and you learn that in rates of reaction. So remember, rates of reaction in organic chemistry is fair game, because if you look at most of these reactions, they do require a catalyst. So for thermal, if I start with thermal cracking, remember what I said, it must be a large hydrocarbon. So if I take, for example, pentane, And what we want to do with the pentane, remember it must start off with an alkane, and it can create just an alkene or it can create two. So we've got pentane, and this pentane can become, for example, it can become propane. So I'm showing you a lot of structural formulas so you can get used to the drawing of these molecules. Plus, so I can end up with propane. And now if I've used 3 carbons, I only have 2 carbons left. So I'll have to create ethene. So you'll see that if I started off with a certain number of carbons, I must end up with the same number of carbons. Okay, so what I want to put here is that if it's thermal, it's taking place at a high temperature and high pressure, and there's no catalyst. If I had catalytic cracking, okay, in that situation, I can start off with an alkane. Let's say I start off with butane. Oops. So I start off with butane, and then butane. Now here's the thing. This does take place with a catalyst. So you list your catalyst above your arrow. And what you can end up with, if I use butane, I can end up with ethane. So there's 2 of my carbons gone. And I can end up with ethane. And because I only have 2 more carbons left, I have to end up with ethene. And I end up with ethene. And remember, your catalysts here is alumina or silica. So there's 2 examples for thermal cracking, and catalytic cracking. And the next type of reaction we have is substitution reactions. Now, substitution reactions, we call them swapping reactions. So here, the atoms in the reactants are replaced by other atoms in organic molecules. So what we want to start off with is saturated compounds like alkanes and haloalkanes. And a hydrogen atom or a functional group is substituted by another functional group on the carbon chain. So there's a swapping of atoms that's actually happening here. So the first reaction we've got here is hydrolysis. Again, make sure you pause the video, take down the notes, and then you can continue. So for example, the base formula is a haloalkane plus a base is going to give me an alcohol and a salt. So for example, I could take bromo ethane plus water, and that could give me ethanol plus hydrogen bromide, or we call it bromic acid. Okay, so if I had to just move this out of the way quickly, let's move it a little bit lower. Okay, all right, so if I had bromoethane plus water gives me ethanol plus, if you're using bromine here, so it will be HBr. Okay, so let's look at where the molecules are actually coming from. So your bromines over there and a hydrogen, and that's going to give you your hydrogen bromide, and your water over here is going to give an OH, so you can get an alcohol out of that. So I started off with bromoethane and I ended up and mixed that with water, and that gives me an alcohol and a salt. So let's just remember that when we talk about the X over here, that is always a halogen. So it's a halide salt that forms there. So that's if I take a haloalkane and water and get an alcohol and a salt out of it. The other option then is if I have a haloalkane and a base. Okay, so in this situation, I can have, again, let's say I have just grab this from here and let's just move it out of the way, just so that it's here on the side. Okay, so what I could have here then, I could have chlorobutane, let's just get a, so I could have 2-chlorobutane plus a base, let's say NaOH, okay? And that's going to give me an alcohol plus a salt. My alcohol here, it keeps that carbon chain. So I'm going to end up with, so you have sodium hydroxide, which is your base. And I'm going to end up with butanol, okay, plus, oops, NaCl. Okay, so if I'm having a look here, I end up with, oops, sodium chloride at the end. So I can have a look again at where everything's coming from, and I can see that my chlorine there and my Na there form NaCl, and your OH here, oh sorry, I forgot to draw the OH, sorry about that. So butanol, your OH is then coming from there. So that is how I have a haloalkane plus a base gives me an alcohol and a halide salt. Now, the reaction conditions for something like this is your base must be dissolved in ethanol and mixed with a haloalkane and heated under some sort of reflux, right? So base is a diluted base. It's diluted, and the solvent that they're using, so here ethanol is the solvent, and mixed with the haloalkane and then heated under reflux. So again, you can add heat to this reaction just above the arrow. You can put the word heat. So those are your two different types of reactions for hydrolysis, and those are your reaction conditions. And remember, reflux just means heated over a long period of time. All right, the next thing you have is the halogenation of alkanes. So what you've got is an alkane, and added to that alkane, you've got a diatomic halogen. So that's what that X represents. You then end up with an alkyl halide. An alkyl halide is basically saying a haloalkane. And over the haloalkane plus a halide salt at the end of this reaction. So if we have a look at an example of halogenation of an alkane, so I can start off with something simple. I must start off with an alkane. So let's say I start off with a basic alkane like methane, and I add that methane to diatomic bromine, and that should give me a haloalkane. Remember, it's substitution, so something has to be substituted, plus I end up with HBr. So I end up with bromomethane and hydrogen bromide, and this is bromine. Okay, so in this situation, if I look here at my alkane, there's a hydrogen. That hydrogen then becomes part of my salt. So that comes from the alkane. And then one of the bromines become part of the salt. And the other bromine becomes part of the alkyl halide or the haloalkane. So in halogenation of alkanes, you're starting off with an alkane, you add it to a diatomic halogen, you end up with a haloalkane and a halide salt. And the reaction condition for this one, it must be in the presence of heat or sunlight. More specifically, it must take place with UV light. So what you can do is, in your equation above the arrow, you can write sunlight, or you can even write UV light if you want. There, you can even write heat. So that's what you want to do there for halogenation of alkanes. All right, the next type of reaction you have under substitution is the reaction of halides and alcohol. So you start off with a halide salt. Remember, again, this X over here is going to represent a halogen. You get plus an alcohol, you're going to get a haloalkane, and you're going to get water out of that. So again, if I use ethanol, or rather we'll start with, I can use hydrogen iodide, plus ethanol, and I should get iodoethane plus water. Okay, so if I start off with hydrogen iodide, I've got HI plus an alcohol ethanol, so 2 carbons, your OH. Please make sure that you fill in all of your hydrogens. It's not just a skeleton drawing. And I get iodoethane, so 2 carbons with their hydrogens and an iodine plus water. And that's your structural formula. So if I have a look at it, I can say that my iodine from the halide salt ends up being part of the haloalkane. I can then say that the OH that's part of the alcohol then contributes to an OH that's now the water. And the hydrogen from the hydrogen iodide, the hydrogen from the hydrogen iodide forms part of the water. And this reaction has to take place in heat. So I can just put the word heat there. It must take place under high temperatures. And that is reactions of halides and alcohols. Alright, the last type of reaction that we look at, and one of the most important reactions, is a condensation reaction or esterification. It's called an acid catalyzed condensation. You start off with an alcohol, a carboxylic acid, and what you make is an alkanoate, which is called an ester, and water. So your general formula for your ester is CnH2n plus 1 COOR. Your R is your alkyl group. So I just want to erase this so that it's not part of the general formula. That's just your general formula. It's part of the COOR, where R is the alkyl group. The polarity, it is a polar molecule. So esters are polar molecules, which means they experience dipole-dipole forces. Esters have a sweet and pleasant smell found in artificial flavorants, perfumes, fruits, and flowers. When we talk about the name of an ester, the alkyl part comes from the alcohol and the alkanoate part comes from the carboxylic acid. The reaction conditions, very important, is you're going to add concentrated sulfuric acid as your catalyst because it's a dehydrating agent. It removes water and it is a dangerous and strong and also corrosive acid. So I'm going to show you an example of how we form an ester. So remember, we must just always remember our base formula: alcohol plus carboxylic acid is going to give me an ester plus water. So for this one, structural formula, very important. Reaction conditions are very important. And also how you name it is very, very important. So remember, you can take any alcohol, any carboxylic acid, mix them together, and you can get this reaction going. So for example, if I took propanol and I added it to ethanoic acid, I should get an ester in water. So if I look at propanol, I've got 3 carbons as my base and their hydrogens. Okay, and it has its OH plus ethanoic acid, which is 2 carbons. Oops. One of your carbons has a double bond here to an oxygen, and it has an OH. Now here's the important part. Your alcohol is always going to give up its hydrogen. Okay? And your carboxylic acid is always going to give up its OH. Now, what happens here is that these atoms form H2O. So that is removed from the 2 molecules. It's going to form the water that we have at the end. So what happens then is, if you can have a look here, there is a opening over here and an opening over here. And what happens between the 2 things of 2 organic molecules over here is that the oxygen from the alcohol bonds with the carbon from the carboxylic acid. Okay, so now when I want to draw out my ester, I'll draw out my carbons for my alcohol. Remember that alcohol is still holding on to its oxygen. That oxygen then bonds with the carbon from the carboxylic acid, and it keeps everything else that it has. Okay, so when I name this, remember what I said with the naming. I go back to the naming. The alkyl part of the name must come from the alcohol, and the alkanoate must come from the carboxylic acid. So that's another thing that we should just note down, that the suffix for an ester is O8. Okay, so when I come down here and I need to name my ester now, remember it's propanol, so it's going to be propyl, and it's ethanoic acid, propyl ethanoate. That's the name of the ester. Okay, so remember the yl part comes from the alcohol, and the O8 must come from the carboxylic acid. And then don't forget, what got removed was water, so plus H2O. So I can have a look here and see that, oops, there's my OH that came from the carboxylic acid, and there's my hydrogen that came from the alcohol. And then that bond in the middle, where I said that the O from the alcohol must bond to the carbon from the carboxylic acid, and that is how I get an ester. Okay. So I can, for example, what I could do now is I could just use, for example, I could use, let's use this butyl ethanoate. If the ester is butyl ethanoate, then the butyl is coming from the alcohol. So the alcohol is butanol, and the ethanoate is coming from the carboxylic acid. And the carboxylic acid would be ethanoic acid. Okay, so I can, if I wanted to, if I had to draw out butanol, so I could draw out butanol and I could add it to ethanoic acid. Let's just go H here. Oh, yes, yeah. So butanol plus ethanoic acid. Then remember, this hydrogen needs to come out and that OH needs to come out. It's going to form water in my products. So when I draw out the ester now, I've still got the original. Butanol still keeps its 4 carbons. Okay, and it keeps its oxygen. I know this is time consuming. I know that it's hard work, but it still needs to be done. It bonds to the carbon that has a double bond to oxygen. Plus water. And this thing is called butyl ethanoate. And that is your ester. So there's another way of looking at it. They could give you the product and ask you to write the structural formula to find butyl ethanoate. So what you've got to remember is that the first part, the aryl part, comes from the alcohol, and the O8 part comes from the carboxylic acid. And then structure it in that way. Always draw it like this so it's easy for you to see each time that what you want to take out in the center between the two is the hydrogen out of the alcohol and the OH hydroxide from the carboxylic acid. So in each one, the alcohol, you need to remove the H atom, and in your carboxylic acid, you need to remove the OH, which is a hydroxyl group. So that's how you want to structure it if you want to make an ester. And I can make all kinds of esters. I can make ethyl propanoate, propyl methanoate, methyl butanoate, propyl ethanoate. I can pick any alcohol and any carboxylic acid, and you can get different esters, and each ester corresponds to a flavor. For example, ethyl butanoate, so taking ethanol and mixing it with butanoic acid will give you the flavor for pineapple. Okay, then the last part is how do all of these reactions connect with each other. What you would have noticed is that I can start out with alkanes and then get alkenes. I can start out with alkenes and get alkanes. I can start off with an alkane and get a haloalkane. I can go back and forth, which means all of these reactions in some way are connected to each other. So I'm going to show you that, and that's the end of this video then. Okay, so this is the last part of how do all of these reactions link to each other. So let's say, for example, I have an alkene. And I want to get this alkene to become an alcohol. Okay, so if I want to go from alkene to alcohol, right, I can do an addition reaction. Now my addition reaction for an alcohol, I can do hydration. Okay. If I want my alcohol to then become an alkene, I can do an elimination reaction. And that would mean I would do dehydration. Okay. Now if I want that alkene to, let's say, become a haloalkane, okay, I could do also, again, I could do an addition reaction. And if I do an addition reaction, I can do halogenation. Or if I wanted to, I could do hydrohalogenation. Okay. If I wanted the haloalkane to then become an alkene, I could do an elimination. I can do an elimination reaction, and I can do dehydrohalogenation. Okay. Now, if I wanted the alkene to become an alkane, so alkene to become an alkane, I could do an addition reaction. And the addition reaction that I can do is hydrogenation. In addition to, I could make an alkane into an alkene into another alkane plus an alkene if I do an elimination reaction. And I can do cracking. Okay. I can then, for example, turn an alkane into a haloalkane. And there I could use a substitution reaction, like halogenation. Halogenation of alkanes. In addition to, if I wanted my haloalkane to become an alcohol, I could use a substitution reaction. For example, I could use hydrolysis. In the same way, I can take an alcohol if I wanted to, and I could turn that alcohol into a haloalkane, and that I would use also a substitution, and that's when I would use reactions with a halide salt. And then let's say, for example, I wanted to make an ester. I know that I can take an alcohol and turn it into an ester using a condensation reaction, which is esterification. So that is how all of your organic reactions are kind of linked to each other. So what you need to be doing is, like I said, I know it's difficult, I know it's hard work, I know that it takes a lot of time and effort to do these videos, but if you actually take the time out and work with it, you'll find that this section can be very, very easy if you are willing to do the hard work and engage with it. So those are all your different reactions, what their conditions are, what their base formulas are, how do you draw structural formula equations, and then how do they all link to each other in some way.